Let's look onto types of block ciphers. Traditionally, we categorize block ciphers in two groups: Feistel networks and substitution permutation networks. But I don't know if this categorization is valid any longer, because for me, the current authenticated encryption algorithms that are permutation based actually does not directly fit into any of these two groups. So maybe we should have the third group saying that permutation based cryptography, but anyway, they might be seen a combination of these two. So we will see a solid example when we will be talking about authenticated encryption algorithms. I will talk about ASCON cipher, and everything will be more clear. But currently, let's keep the tradition and let's divide the block ciphers into these two groups, namely Feistel networks and substitution permutation networks, which is short as SPN. So designing a very complicated algorithm is itself a complicated process, but it is also hard to analyze. So when we are designing a symmetric key encryption algorithm, first, generally, we design a round, then repeat this process many times. So a cipher mostly consists of the repetition of a round R times. So this will be more clear when we'll be seeing solid examples. Also, we are using a secret key, and we have to use the secret key information inside this rounds. And you can maybe use the whole key in the round, in every round, in the same way. But such symmetry sometimes causes weaknesses in ciphers. So for this reason, most of the time we have key schedule algorithms. So instead of using the key directly in every round, a key schedule algorithm is used to generate round keys from the secret key. So this key schedule algorithm also requires a few computations. So for this reason, in the lightweight algorithms, these key schedule parts are sometimes very simple. Some lightweight algorithms don't even have a key schedule algorithm. They simply use the secret key and XOR it with the round input. So, but of course, sometimes that kind of simple approach might cause weaknesses in the cipher. So initially, I mentioned this before, lightweight block cipher algorithms focused on low hardware footprint. So their main aim when designing these algorithms was to have an algorithm so that it requires less gate equivalence to implement it on the hardware. So earlier designs like Present, HIGHT, and Cipher, all of these three algorithms are ISO standards, focus on low hardware footprint. So their main aim was to beat AES in terms of gate equivalence, but also have good performance. So Present and Cipher are the only two ISO standards for lightweight block ciphers. HIGHT is a standard for block cipher, so it is in the different category than Present and Cipher. As far as I know, it was designers wanted it to be also a lightweight block cipher standard, but some of the attacks for this cipher make it. I mean, this algorithm couldn't become a lightweight standard because of the cryptanalysis results obtained at those times. Actually, as far as I know, I'm also responsible for that because my master thesis was about the cryptanalysis of HIGHT. But nowadays, as we already mentioned before, you cannot only look at the hardware footprint because we also need fast speed. We have to look at the throughput. We have to look at the latency. We have to look at other criteria like side channel attacks, side channel resistance, and so on. So newer lightweight algorithms focuses not only on the low hardware footprint, but we have other algorithms focusing on other criteria. For example, we have 3 lightweight block ciphers here, and they're focusing on low memory consumption on small embedded processors. And the examples are I2B, Pride, and SPEC. And we also have an algorithm that is focused on the low latency. And there are also algorithms in the literature which has some kind of side channel protection, like Zorro and other LS designs. So in the last years, instead of focusing on the low hardware footprint, designers chose to focus on other areas like low latency or again low memory consumption and so on. So currently we have a lot of algorithms designed for different purposes. Actually, this was also one of the reasons NIST is having a competition so that the winner can be a standard and the IoT manufacturers can only implement that, or if there are more winners, those algorithms, so that we can have a standard that every device has the capability to perform the operations. So these are the some examples. Actually, I can maybe give more than 20 more names of block ciphers that are designed in the last 10 years. But we have these ISO standards currently, so we will be talking all of these 3 of them. And in the future, when this competition ends, but the winner, I mean, the competition is about authenticated encryption. So in the week of authenticated encryption, hopefully we will be talking about the standard that is accepted worldwide. So let's start with Feistel networks. Recall that we kind of categorized block ciphers into 2, Feistel networks and SPN. Feistel networks was introduced by Horst Feistel. A round of a Feistel network consists of 2 operations, a round function and the swap operation. So idea is as follows. The block size, which is b bit, so your input is b bits, it is divided into 2 halves, sometimes referred to as right and left parts. Round function is applied to one half and the output is XORed to the other half. Then the places of these halves are swapped. Key material is generally used inside the round function. So I tried to draw a picture here of a Feistel network. So this is your plain text block. We divide it into 2 parts, left and right. So you have your secret key here and you have a key schedule algorithm, and this key schedule algorithm provides you round keys and they will be used in the corresponding rounds. So your right part comes here, a round function is applied to it, then the output is XORed to the left part. And this modified left part becomes the right part in the next round. And the right part becomes left part in the next round, but it is not affected, as you can see. But it will be affected in the second round. So at the end, you obtain your ciphertext block. Most of the time, we don't perform the swap operation at the final round because cryptographically, this doesn't have any protection at all. Anybody who captures the ciphertext block can perform that swap operation, inverse of that swap operation. So most of the time, we omit this part. So the most famous Feistel example is probably data encryption standard. It was designed by IBM in the 1970s. It was based on an earlier design by Feistel. In 1976, there was a call by NIST, and this was submitted to there to become a federal standard. And NSA tweaked this algorithm by modifying its S boxes, but this modification actually provided more security because they knew the differential cryptanalysis technique at the time, and they made the ciphers secure against this kind of attacks. But they also shortened the key, which actually made exhaustive search attacks possible in the short time, let's say. So and maybe it wasn't that easy to do 2 to the 56 encryption operations in 1970s, but at the 1990s it became easy to perform this many operations because of the technological advancements and the speed of personal computers and so on, this become easier to do. So currently this is known as data encryption algorithm, not the standard, since it is no longer a standard. And this is important because a lot of people still think that this is a standard and it is secure to use it, but it is not. Because it became useless after 1990 since its short key is susceptible to brute force attacks, which we already mentioned in this course. So it has a Feistel structure. You have the plain text, you have an initial permutation which has no cryptographic significance. So left part and right part. Right part is first extended to 48 bits, XORed with your round key, which is obtained from the master key, but two permutations and rotation operations performed before obtaining the round key. Then you have this round function here, which is shown in the next slide like this. So your 32 bits extended here, XORed with your round key, and this is the round function. In the previous picture, we represented as, I think, as simple as C. So your 48 bits are provided as input to 8 S boxes, which take 6-bit inputs. All of these S boxes are different. Then but they provide 4-bit outputs. So you again reduce to 32 bits from 48 bits. Then there is a final permutation, and the result is XORed to the left part. If you go back here, this was the part I was talking about, and the result is XORed to left part. In the next round, as the Feistel type works, this becomes the right part, and the right part becomes the left part, and you perform this operation. And if we go back, as you can see, DES has a block size of 64 bits, key length is 56 bits, and number of runs is 16. So this operation is performed 16 times. So this is a very simple structure, but we are not going into details because this is not a lightweight design. But in this course, we want to focus on the lightweight designs. So instead, we move on to ISS standards of block ciphers, which are lightweight, and we start with HIGHT. HIGHT is a lightweight block cipher designed by Hong et al. In 2006. It is shown to be highly convenient for extremely constrained devices like RFID tags and sensor networks. It became a standard encryption algorithm in South Korea. It is also IEC standard for block ciphers. It is a generalized unbalanced Feistel network. This will be more clear in the picture when I show you the structure of HIGHT, but it means that instead of two lines, as we call this left and right part, this time you have more parts. So this is why we call it a generalized Feistel network. And the swap operation does not swap the half of it, but some part of it. So this is why it's called unbalanced, but it is not that important. So the block size is again 64 bits like this, but the key size is now 128 bits, and the number of runs is 32. And you can find the paper which was published in the CHES conference. So in the paper, designers compare their hardware implementations with AES. So as you can see, they reach to the any hardware implementation where they only require 3,000 gates, and their the algorithm they compare, sorry, the implementation they compare at the time required 3,400 gate equivalents for the AES implementation, and the throughput was a lot less than the HIGHT performance. But of course, these are two different technologies, as we already mentioned a lot in this course. It is not easy to compare different implementations, different technologies. And even we have to look at the device that is implemented, because some operations might be easier on some FPGAs and it might be harder on some other FPGAs. So such a table does not say much. And also we have implementations where people implemented AES which required less than 3,000 gates anyway. So Lim et al. Reduced this implementation to 2,600 gates. but probably that would also result in a less throughput. But also Rin et al. Showed that height is faster than AES, DSL, CT, and XT on 8-bit microcontrollers. So this design was somewhat faster than AES on some small constraint devices. So this was the claim of the designers and some other academicians. So the general picture of height is as follows. You have the plain text block. You perform initial transformation, which is just XOR of the input with some whitening keys. Then you perform the round operation, but every round you only use 4 bytes of the round key, which is obtained from the master key. So from master key, the key schedule actually provides you 4 bytes of round keys, which you use every round, and finally you XOR it with the whitening keys and obtain the ciphertext block. So this is the bytes of your master key. Since you have 128 bits, this means that you have 16 bytes of master key, and from these bytes you actually obtain the following whitening keys and round keys, which are referred to as subkey. So this means that if you know the first byte of your master key, then you also know this whitening key and this 8 subkeys bytes. So actually, in the cryptanalysis, most of the attacks focus on capturing these bytes and so that knowing all of the related subkeys. So the structure is as follows. Your block is here. So in this picture, every line actually represents a byte because we have 64 bits here, which is 8 bytes. For this reason, we have 8 lines. And as you can see, this is why we call it a generalized Feistel network, because we have more than 2 lines here. And the swap operation actually rotates the output 1 byte to the left, as you can see. So the algorithm is really simple. You have for instance, here you have your byte here and perform F0 operation here. Then perform a modular addition, which is just a regular addition of bytes, but it will be performed in modulo 2 to the 8, because you cannot have a result that is larger than 8 bits because it would overflow. So this represents modular addition, and this represents XOR operation. So you have F0 function, which I will show in a minute, but you also have F1 here, and the addition operations swapped, as you can see. Here you have modular addition, then XOR. Here you have XOR, then modular addition. And actually this part is almost identical to this part. And these are where you put your subkeys. So what is F0 and F1? It is just simply an rotation and XOR operation. So let's say that X is your input to F1. This means that you XOR X with itself 3 times, but not itself directly, but rotations of it. So this means that 3-bit rotation to the left. This is 4-bit and this is 6-bit. And F0 is somewhat similar. So as you can see, there are very small number of operations here. So actually, with such small amounts of operations, it is not easy to conceal your plain text. This means that you cannot have much confusion and diffusion with such a simple round function. This is why we have actually 32 rounds of height to provide security. But again, as I told you before, in literature, we have many attacks that breaks more than 20 rounds of this cipher, and in the related key setting, there are attacks that break the whole cipher, which are somewhat faster than exhaustive search attacks. So attacks always get better and better. So since we can find such weaknesses, we just suggest that there's no point of using HIGHT if you have something that you are more confident and feel that it is more secure. So most of the time, I don't suggest the usage of HIGHT in practice.